Hi, I'm Miriam Shinichi. I'm an assistant professor at USC Electrical Engineering and Neuroscience, and today we're going to talk about brain-machine interfaces in our session. So as you know, our brain consists of 86 billion neurons, and it's the activity of these neurons that represent our emotions, thoughts, and action. In particular, not only are our brain's functions, such as movements, represented in neural activity, but so are its dysfunctions, for example, in neuropsychiatric disorders like depression, or even in induced states such as anesthesia or coma. So the question is, what if we can actually build a direct interface to the brain, record the neural activity? Can we build brain-machine interfaces that can help us treat neurological disorder or even understand how the brain works better? And of course, there's many challenges that we have to overcome before we can have a brain-machine interface. The first challenge, obviously, is to have a technology that allows us to record brain activity. And you can think of these recording at various levels of invasiveness and spatial-temporal scales. For example, a very non-invasive modality that you can think about is an electrode cap that you can wear that records a modality that we call EEG. But this is going to have very low signal-to-noise ratio and not enough spatial resolution. So then on the other extreme of invasiveness, you can imagine microelectrode arrays that penetrate the cortex to give you the finest spatial resolution so that you can actually record the activity at the level of single neurons, an activity that we call the spiking activity that represents the presence or absence of an action potential. And because it's a binary event, we usually represent it as a binary time series. And there's modalities, of course, in between. But we don't just need a recording technology. We also need to be able to write in information potentially by having a stimulation technology, either electrically or optically. So let's say we have these technologies, and we're going to get a ton of data from very high-dimensional brain networks, and we have to make sense of it. So the next challenge would be, how do we use the data that we collect from the brain to infer a state of the brain? And because we want to build a technology that interacts with the brain, how can I use methods from control theory to control brain states? So you can have tools from machine learning, statistical inference, and control theory brought into the field to develop these types of algorithms. And then finally, once we have these algorithms, of course, we have to have an implantable device. And this device has to be wireless, low power, efficient, and biocompatible. So there's a lot of challenges on the side of integrated circuits that people are working on. So as you can see, this is a truly interdisciplinary field at the interface of neuroscience, neurosurgery, electrical engineering, statistical inference, control, biomedical engineering. And really, the field is quite diverse in the sense of people with various expertise that try to build these systems. And today, you're going to hear from three of us that almost cover the entire spectrum. I am by training an electrical engineer who worked on statistical inference and control theory and then got fascinated by neuroscience and entered the field. So my talk is going to be a little bit motivated by that engineering lens. Okay, so what we're going to focus on in our session is how can we use brain-machine interfaces as a technology to treat neurological disorders, and then as a tool, a scientific tool to understand how the brain functions. To understand what a brain-machine interface does, let's go back to the first instances of brain-machine interfaces that started to be developed about 20 years ago. So these brain-machine interfaces were developed to turn thoughts into action with the goal of restoring movement in paralyzed patients. So in a lot of neurological injuries and diseases that you have, the patient still retains the ability to plan and think about movement. But the problem is they can't communicate that to their muscles. So in these cases, the idea was that we can record electrical activity of the brain from motor cortical areas and then take this neural activity into a mathematical algorithm that we call the real-time decoder, and then infer from the neural activity what the intention is, turn it into a control command to move, say, a robotic arm, and then in the process provide visual feedback to the subject. So if you think about this brain-machine interface, or BMI for short, is providing a direct control link from the brain to the prosthetic. Now, if you go back to kind of engineering systems, if you think about flying an airplane, What a closed-loop autopilot does is it's, let's say, trying to take the aircraft to a particular desired altitude, and it does that using a closed-loop controller by knowing where the current altitude is, where the desired target is, looking at that error signal, and then sending a control command in the form of an engine thrust to get you to the desired altitude. And this is exactly what we are trying to do with the brain-machine interface, except that here, the controller is the brain, the thing to be controlled is the prosthetic, the control command is the neural activity, and the feedback, say, is the visual feedback. You see where your arm is going, you want to take it to a certain place, so you can issue corrective actions or feedback control actions. But before we can build this closed-loop control system, we have to have a way to estimate what the intended movement is based on the neural activity. So how do we do that? In general, what we do is we build a model that we call the encoding model. So this encoding model will tell you how this movement, which is the intended movement of the subject, is represented in neural activity. So in effect, what it's doing is giving you a distribution of the activity given the intended movement and some model parameters. And we have to, of course, learn these model parameters and problem that we call system identification. Once we learn this model and these parameters, then what we do is we develop a decoding algorithm, which is really an inverse map of the encoding model and gives us a distribution on the likely intended movement given an activity that you observe and the learned parameters. So why is this problem so difficult? There are multiple things that make it very difficult. First, we know that neural activity is very high dimensional and noisy. It's non-stationary and it could change over time. The very intended movement that you're trying to build a model for is hidden. I don't know what the intention is. It's hidden from my view. So how do I actually have the teaching signal to even learn this encoding model? And finally, if you want to model spiking activity, these are not normal signals like wireless signals that you have. These are very specific binary time series happening at a very fast time scale, so you have to have the proper statistical models. And despite all of these difficulties in the last 20 years, there's been a lot of labs doing fantastic work, and we've made significant progress to the point that now we have clinical trials with human subjects thinking about a movement and by which they're able to actually retain some sort of movement of a robotic arm. So here's one such subject. So he's just thinking about the movement and trying to eat a piece of chocolate. And this is work done at the University of Pittsburgh.
It's falling out.
She's gonna try again, of course. So you can see that she can make the movement, but of course there's a lot of room to make progress, right? If you think about eating yourself, it's probably much faster.
You can drop it on my hand.
Oh, dang
Drop it. There we go.
One small,
That doesn't work
one
so well.
small nibble for a woman, one giant bite for DCI.
There you go. So you can see it's pretty motivating to see these patients actually regaining some movement after years of paralysis. But there's still a lot that we can do to have dexterous movements and proficient movements that mimic those of our own arms. But what is next really for the field is to allow such control for dexterous three-dimensional naturalistic movements like the movements that you saw Jen make in that video. How can we improve these algorithms to allow us to do more naturalistic movements? Moreover, you can imagine scenarios in which you don't just want to control an external device. The limb is intact and you want to allow the subject to control their own arm. So can we combine decoding with, say, spinal stimulation or muscular stimulation in order to restore movement to the native limb? And there's been fantastic work in recent years showing proof of concept that this is doable, but we still have a long way to go. And finally, can we use these BMI systems as a new scientific tool to understand how the brain learns to control movements? As I mentioned, Aaron would go in depth into that subject. All right. So far I talked about this one type of BCI that is for control of external movements to restore movement in paralyzed patients. But in many neurological disorders, you kind of need to also be able to manipulate the diseased brain state. Let's think about depression. In this case, there's a subject whose brain activity causes them to be depressed and have very low mood. So there are proof of concept demonstrations in open loop studies showing that if you electrically stimulate the brain, you can potentially alleviate depression symptoms. And this has motivated a next generation of BMIs that kind of try to do the opposite of what I already showed you. So instead of trying to let the brain directly control an external device, now we are trying to control the state of the brain itself by developing a controller on our end. So let's go back to our airplane example. In this case, as I mentioned, we wanted to control the altitude of the airplane based on feedback of its current state, what the target is, and using this controller to issue control commands in the form of engine thrust. This is exactly what we would do, for example, for depression. The idea is that now the plant to be controlled is the brain. The control command is, for example, electrical stimulation. The feedback is the neural activity that I observe from the brain. And for example, from that, I can decode what the current mood is. I have a desired mood state that I want to go to, and I use a controller to go there. And you can extend this to various neurological disorders such as epilepsy, Parkinson, OCD, addiction. We can think about developing these systems to have alternative treatments for subjects who are otherwise not responsive to medication or psychotherapy. But why is this problem hard? First, we have the first problem that I mentioned. We have to decode the brain state. In this case, let's say the mood from neural activity. But we have to go one step further. We also need to know how to manipulate neural activity. Basically, not only describe how neural dynamics work, but also how input affects those dynamics. And this is extremely challenging because, again, we have high dimensional inputs and outputs. In some cases, the output is unknown because we don't know what the neural signatures of these disease states are. We have no idea. The relevant input could be unknown because we don't know what stimulation parameters are going to make the subject feel better. And then we can build the most complex model, but they may be useless in the sense of closed-loop control because they're not amenable to real-time control. And finally, matters are made worse by the fact that the brain is plastic and time-varying. So you can see there's so many challenges that we have to solve algorithmically. So on the side of depression, in the recent years, as part of a DARPA Subnets project and in collaboration with Eddie Chang, who's also a speaker in this session, we've been trying to actually develop decoders that can track mood in real time from human brain activity. Again, the solution is the same. Let's try to build an encoding model and a decoder. And what we have shown is that we can indeed track mood in real time from human subject. And moreover, we can find what are the brain regions that are most critical for such decoding to be achieved. Now let's say I have a decoded mood. This is just the beginning. It serves as a feedback signal. What I have to do next is to model how electrical stimulation affects these neural biomarker, which is the biomarker for the mood state, right? And there's a lot of tools that we have to bring in from system identification theory in engineering, design optimal stimulation patterns that can excite the brain across all frequency bands such that we can build an accurate model. And we've been working on developing a signal that we call a binary noise signal that can help achieve that. And once you build your model, you can see the prediction of a neural feature versus the true feature on the right. So we can, to some extent, track the drifts of these neural features in response to stimulation. All right. So what we've seen in the session so far is BMI as a technology and two types of it for control of external devices and for control of the brain state itself. So our session is going to go much more in depth about what I just talked about. So on the science side, BMIs as a scientific tool, we're going to have Aaron from University of Pittsburgh telling us how we can use these BMIs as a controlled system to learn how the brain controls movement. And then on the technology side, Eddie Chang from UCSF is going to tell us about a different type of BMI for control of external devices, this time to restore speech to subjects with severe neurological disabilities. All right, so with that, I would like to invite Aaron to come and start the next part of the session.